If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in the methods of impulse and momentum, we discuss about collisions and particularly head-on collision. Actually, term collision is very badly understood. Actually, what we understand by the term collision as a first instance that bodies which make collision make contact also. Actually, it is not necessary that bodies undergoing collision make contact. There may be strong repulsive forces between the bodies. Even that event is called collision. Actually, what happens in collision? The bodies undergoing collision apply very large forces on each other. That forces may be direct contact forces. In this case, the bodies make contact. These forces may be strong repulsive forces. In this case, the bodies will not make contact. And other thing, duration of the collision must be much smaller than other time scale of motion. That is, motion time scale before collision and after collision. So such kind of event are called collision. Now let us discuss a very interesting apparatus example that is called Newton's cradle. Here you can see initially these four balls are hanging stationary. This ball comes and strike this ball, and mysteriously this ball jumps. Actually, what we can say at present, perhaps energy of this ball is transferred to this ball, then this ball to this ball, and this process repeats. But how this happens, we'll able to understand after studying head-on collision. So before in a head-on collision, what we do, we first define what is collision and under what condition an event will be called collision, and then we start step-by-step analysis of collision process, particularly head-on collision process. Collision or impact. Another name of collision is impact. What is collision? Let us see. A collision or an impact is an interaction of negligible duration between two bodies in which the bodies apply relatively large forces on each other. Here two things are very important: negligible duration and large forces. I had told earlier that meaning of negligible duration is that the duration of collision should be neglected or must be negligible as compared to other time scale of motion. And what we mean by large forces between the bodies, that as compared to these forces, other external forces can be negligible or should be negligible. Let us define them one by one. Interaction forces during a collision are created due to either direct contact or strong fields or some connecting links. So if the interaction forces are created by direct contact, in this case the bodies undergoing collision make contact. If the interaction forces are created by strong fields or some connecting links, in these cases the bodies undergoing collision will not make contact. Let us come, what about duration? Duration of a collision should be small enough as compared to the time scale of interest as to consider only the states of motion immediately before and after the collision and not during the collision. Actually, what is mean by time scale of interest? Actually, when we study the bodies under collision, we study them when they are some apart and moving, and when they are moving there is no interaction force between them is negligible, or you can say there is no interaction force. And with that state, the bodies start interacting, and after some time the interaction ceases. So the time during which the interaction between the bodies exists, it is called duration of impact or duration of collision. But before the collision, the bodies cover any observable distance. Time taken in that should be much larger than the duration of impact. In this way, duration of impact is neglected in all kinds of collision. Duration of a collision ranges from 10⁻³ seconds for collisions of elementary particles to millions of years for collisions of galaxies. The collision observed in the terrestrial world, like that between two balls, lasts for few milliseconds to few seconds. So that is a typical duration of collision. Between elementary particles, the collision may have this much smaller time, or between galaxies, The collision may require billions of years. But at present, we are not going to in such extreme example. We start discussing collision with examples of collision between terrestrial bodies, say between two balls, between a ball and a bat. Such collision last or duration of these collisions ranges from a few seconds to a few milliseconds to a few seconds. Line of impact. So now we come some important terms while defining or while analyzing collision. What is line of impact? Actually, the bodies which apply forces on each other. These forces are Newton's third law pair. So they must be collinear, equal in magnitude and opposite direction. So line of these forces is called line of impact. Actually, in terrestrial body collision, when bodies make contact, what we can say, when they make contact, at the contact point, we can draw the common normal. And if frictional forces between the bodies are avoided or neglected, or there is no friction, the interaction forces will be only the normal reactions. So this common normal is called line of impact. Actually, we will see later that in all collisions, friction is always neglected if it is not stated to consider. Say here, we consider these two bodies, they are making collision. So they may consider two stones, so they will make contact during collision. So here at the contact point, we can draw a common normal, and this common normal is called line of impact. And we can draw a tangent also, and that tangent at the contact point will be a common tangent to both the bodies. So we call it common tangent. The common normal at the point of contact between the bodies undergoing collision is known as line of impact or line of collision. The tangent drawn at the point of contact is known as the common tangent. One more thing, friction at the point of contact is usually neglected until it is stated to be considered. Actually, while analyzing collision, we define a term that you might be knowing, that its name is coefficient of restitution. And we define collision in terms of coefficient of restitution. It depends on elastic properties of the body. Actually, in the definition of coefficient of restitution, effect of frictional forces is not considered. So it is a convention that in all kinds of collision, we ignore the frictional forces. And I said it is convention. Actually, in any of the collision problem, it is not said that you have to neglect friction. You have to automatically neglect friction. That is what is meant by convention. Central and eccentric collision. So this is two types of collision: central collision and eccentric collision. Let us see what they are. In a central collision, mass centers of the bodies lie on the line of impact, whereas in an eccentric collision, mass centers of at least one body does not lie on the line of impact. What does it mean? That we can understand by situation. Say here, these are two bodies undergoing collision. So in this case, the mass center of this body C1 and mass center of this body C2 lies on the common normal and line of impact. Such a kind of collision is called central collision. And what is eccentric collision? Mass center of at least one body or both the bodies will not lie on the line of impact. Let us see, for example, here we have considered here C2 is not lying on the line of impact. So this kind of collision will be eccentric collision. What will happen in eccentric collision? It is very common sense example. That is this normal force of this first body will not change state of rotation of this body because it passes through mass center. But in this case, this normal force will change state of rotation of this body. So in eccentric collision, state of rotation of the body is undergoing collision changes. So this kind of collision can be analyzed after studying rotational motion. So we'll postpone analysis of eccentric collision after the rotational motion. In a central collision, state of rotation of either of the bodies remains unchanged, whereas in an eccentric collision, the state of rotation of the body, mass center of which do not lie on line of impact, changes. Actually, of which body state of rotation change? Whose mass center is not on the line of impact. At present, we discuss only central collisions and postpone discussion of eccentric collision after rotational motion. Actually, in eccentric collision, state of change in rotation is involved, so that can be analyzed only after rotational motion. To ensure a collision to be a central collision, in every prototype example, colliding bodies are considered to be spheres or disks. Actually, this is why you might have seen that all the examples given in all the textbooks in collision, the bodies which you take are either sphere or disk. Actually, what is the condition of a spherical body or a cylindrical, that is a disk, circular section body, that it normal always lie their center. If the bodies are uniform, it means the common normal pass through their mass centers also. So in this way, if we consider collision between uniform spheres and uniform disk, that will always be central collision. Again, if it is not set, the body is assumed to be uniform. If the body is non-uniform, it will be mentioned. So it is again a convention. If we say a body of mass m, so we have to assume it to be uniform. The line of impact and common tangent are also known as n-axis and t-axis. Actually, you can see here, these two lines, common tangent and the line of impact, are mutually perpendicular. So they can be considered as a Cartesian coordinate axis. But here we could not call them x and y axis. What we call the common normal as n-axis and common tangent as t-axis. Head-on and oblique collisions. Actually, these two terms represent two different types of central collision. As the name oblique collision, it is obvious that the velocities must be oblique to each other. It means there must be some angle between the velocity vectors. If it is so, then at least one or both the velocities vector cannot lie along the common normal. And opposite to that, in head-on collision, both the velocity vectors lie along the common normal or line of collision. So let us define and understand these two types of collision one by one. Head-on collision or direct central collision. Actually, direct central collision is another name of head-on collision, but it is very rarely used. So I have mentioned this name here so that whenever you find this term, just identify it as a head-on collision. In a head-on collision or a direct central collision, the velocity vectors of the colliding bodies are directed along the line of impact, that is the common normal. So as I have said, in head-on collision, both the velocity vectors, means velocity vector of both the colliding bodies, must lie along the common normal. Say here as an example, in the first figure you can see these two bodies are colliding. Mass centers of these bodies are along the common normal, so they are central collision. And velocity vectors are along the common normal. So what is the required condition for a head-on collision? That is, mass center of both the bodies must lie on the common normal and both the velocities vector must be along the common normal. They must be, or they may be in the same direction, or they may be in opposite direction, as in the second case. And as contrast to this head-on collision, let us see what will happen in an oblique collision. Oblique collision. In an oblique collision, velocity vector of both or any one of the bodies are not along the line of impact. Say in this case, in the first figure, the velocity vector of the second body u2 is not along the line of impact, it is making some angle. In the second case, velocity vectors of both the bodies are not along the line of impact. So both kind of collisions are called oblique collisions. Process of head-on collision. Actually, we have defined what is a head-on collision and what is oblique collision. So it is obvious that analysis of head-on collision will be simpler than the analysis of oblique collision. So today's talk or today's lecture, we concentrate only on the head-on collision. So before we proceed with the analysis, let us try to understand what is happening during an head-on collision or process of an head-on collision. To explore the process of a head-on collision, consider two balls A and B of masses ma and mb moving with the velocities ua and ub in the same direction. Velocity ua is assumed greater than ub for the collision to take place. Final velocities of the balls after the collision are denoted by VA and VB. So these are the notations we are making, and we'll use this standard notation throughout our course. Again, the velocities before the collision we represent by U, and velocities after collision we represent by V, and of which body by the subscript name for that body. And masses of the bodies are assumed MA and MB. Say here, when the bodies make contact, again I'm saying we are discussing we are concentrating our discussion to the collision of terrestrial bodies. Actually, principle involved in the collision of terrestrial bodies where the bodies make contact, and other kinds of collision where bodies do not make contact are the same. But these kind of collision when bodies make contact with each other, they are intuitively easier to understand. So we are taking example of such problems. So here you can see these two bodies. Here UB is assumed smaller than UA, so that collision will occur. So when the bodies make contact, we'll say beginning of collision, or interaction between the bodies starts. So that is beginning of collision. So that short-term duration interaction is called collision. So when interaction starts, that is called beginning of collision. And here when interaction starts, because of the interaction forces, these bodies will get deformed. And this deformation process will keep on increasing. Till the deformation process is increasing, velocity UA will be greater, velocity of this ball A will be greater than that of ball B. But when the deformation will be maximum, both the bodies will have same velocity. So this state we call maximum deformation. Thereafter, the deforming forces will start decreasing, but they will be in the same direction. So again, velocity of the ball B will keep on increasing, and that of ball A will keep on decreasing. And when the interaction between the bodies ceases, means when there is end of collision, the bodies acquires, the second body acquire velocity VB, and the first body acquires a velocity VA. Again, for to interaction cease, what is necessary? Either VA will be equal to VB, or VB must be greater than VA. So these are the two conditions. So before the collision, UA must be greater than UB. But at the end of collision, either both the velocities must be, or either both the velocities are equal, or velocity of body A is greater than that of velocity that of body B. During collision, both the bodies apply deforming forces on each other. The deforming forces first increases, causing deformation to increase till deformation forces and deformation both become maximum, and velocities of both the bodies become equal. Say U. This period is known as period of deformation or deformation period. So from the beginning of collision or beginning of interaction to the instant when deformation is maximum, or interaction forces between the bodies or deforming forces are maximum, bodies require same velocity. This period is called period of deformation, or you can say deformation period. And after that, the deforming forces start decreasing, and deformation will start decreasing from maximum deformation, and till the moment when interaction between the bodies ceases or end of collision. This period is called restitution period. So let us see, immediately after the maximum deformation, the deforming forces begin to decrease, causing the deformations to decrease till the deforming forces vanish and deformation ceases to decrease. At this instant, the collision ends and both the bodies acquire their final velocities, VA and VB. This period is known as restitution period. So from the instant of maximum duration to the instant of end of collision or end of interaction between the bodies, the period is called restitution period. Depending on the maximum deformation and elastic properties of their materials, the bodies may recover partially or fully from their state of maximum deformation. And actually, whether the body will recover from the state of maximum deformation fully or partially, it will depend on two things: the maximum value of deforming force and elastic properties of material. Actually, for simplicity here, I have shown here, or actually it is for simplicity, it is assumed that at the end of collision, the bodies are recovered fully from deformation. Actually, it is not necessary. When the bodies will recover fully from their deformation, the collision is called perfectly elastic collision. When the bodies will recover partially from the state of maximum deformation, the collision is called inelastic collision. And when bodies will not recover at all from the maximum deformation, the collision is called perfectly inelastic collision. Analysis of head-on collision. Now we are in a state to apply the principles of physics, either Newton's law or work energy or momentum method, to analyze collision. As we have mentioned earlier, that for impulsive event, collision is an impulsive event. The most suitable method is to apply impulse momentum principle. So to analyze collision, we apply the impulse momentum principle, and we also consider the detailed process. Only when we will be able to apply the impulse momentum principle and complete analysis of a head-on collision. So denoting the deforming forces by D and R during the deformation and restitution period, we apply the impulse momentum principles. Actually, from the elastic properties of material, it is a very well-known fact that if deformations are up to elastic limit during deformation process and during restitution process, the deforming forces will be equal for every deformation. But if the deformation are beyond the elastic limit, the bodies will not recover fully from the state of maximum deformation, and when the restitution period for the same deformation as we had in deformation process, the deforming forces are unequal. And for these are the fact why we are assuming, we are giving different symbols to deforming forces during deformation period and during restitution period. As the name suggests, during deformation period, the deforming forces we are denoting by D, and during restitution period we are denoting these forces by R. So first we begin the beginning of collision. So you can see the same notation: velocity UA, velocity UB, and UA is greater than UB. Now that is state of maximum deformation, and we consider end of collision, when interaction between the body ceases or deforming forces ceases to act. From this instant to that instant, that is called period of deformation, or you can say deformation period. And from here to here, we call it is restitution period. And during deformation period, the interaction forces or deforming forces we are denoting by D. So let us see here, deformation is not complete. You can see here deformation is smaller than this maximum deformation. On this body apply deforming force towards left, say this. This deforming force is on body A due to body B. Similarly, deforming force on body B due to body A will be towards right, this way. In the same way, we can show the deforming force during restitution period. So here, the deformation is not maximum, it has recovered somewhat. So deforming force on body B by body A will be towards right, and on body A by body B will be towards left. So here, see, this R is the deforming force during restitution period on body A due to body B. And similarly, this is the deforming force during restitution period on body B due to body A. So now all the forces we have considered, and we have seen all the velocities are mentioned. So for the deformation period and for the restitution period, we'll apply the impulse momentum principle and write the equations for body A and body B separately. And for the purpose, we should draw the impulse momentum diagram. So here we draw the impulse momentum diagram, And here parallelly we write the impulse momentum equations. So first we apply the impulse momentum principle on body A. So let us draw the impulse momentum diagram of the body A. So initial momentum is MAUA, and impulse of this force is equal to this momentum MA into U. So here initial momentum MAUA plus impulse of deforming force, that is this force is acting on body A, so this is impulse, equal to this momentum MA into U. So that is impulse momentum diagram of the body A during the deformation period. So accordingly you can write the equation what? MAUA minus ddt integral is equal to MAU. Actually I have not shown here the limits of integration, just for clarity, that is for better readability of diagram. Actually this integration extends from the beginning of collision to the maximum deformation. So let us see the equation. MAUA minus ddt is equal to MAU. Again I mentioned here this integral is definite integral. It extends from the instant of beginning of collision to the instant of maximum deformation. Now we draw the impulse momentum diagram for the body B during the deformation period. You see from here the initial momentum of body B is MBUB, and we add the impulse of this deforming force, and the final momentum will be MBU. So let us see impulse momentum diagram. Initial momentum of body B MBUB, and impulse of deforming force will be towards right. So this ddt is equal to final momentum MBU. Again this integral I will again mention that extend from the instant of beginning of collision to the maximum deformation. So relevant equation will be what? MBUB plus ddt is equal to MBU. So let us see here. MBUB plus ddt integral is equal to MBU. Let us call equation number 2. Similarly, we draw the impulse momentum diagram of both the bodies one by one for the restitution period and write the impulse momentum equation. Say for body A during restitution period, MAU is the initial momentum, impulse of this force is the impulse, and MAVA is the final momentum. So what is impulse momentum diagram? MAU, the impulse of deforming force RDT towards left, and final momentum is MAVA this way. So what will be equation? MAU minus RDT is equal to MAVA. MAU minus RDT is equal to MAVA. Equation number 3. Again I mentioned here that this integral is definite integral. It extends from the instant of maximum deformation to the instant when interaction between the body ceases or collision ends. Similarly, we can draw the impulse momentum diagram of the body B. See here, for body B, initial momentum in the restitution period is MBU, and impulse of this force R towards right, and final momentum is MBVB. So impulse momentum diagram is MBU, initial momentum, and impulse of R is towards right. So RDT is equal to MBVB. So here this please write VB. So there is a typing error. So that is we can write now equation MBU plus RDT is equal to MBVB. So these are the 4 equations. Now with the help of these 4 equations we can analyze the entire collision. Actually here you can see the beauty of the impulse momentum as well. Actually you don't know how the deforming forces vary with time during deformation process and restitution process. Even then we are able to write their effects. And actually the forces, how they vary on time, and in other words, we don't know the value of these forces from instant to instant during the collision. So we are not in a position to apply Newton's law. That is why we are applying here impulse momentum principle. Impulse momentum equations. We write all the 4 equations for reference. That is 2 equations for the process of deformation, one for the ball A and other for ball B, and next 2 equations for the process of deformation, one for the ball A and other for the ball B. Let us see. MAUA minus DDT is equal to MAU. Equation 1, that is impulse momentum equation for the process of deformation on the ball A. Similarly, MBU plus DDT is equal to MBU, equation 2, that is impulse momentum equation for the process of deformation on the ball B. Similarly, we write MAU minus RDT is equal to MAVA. That is the impulse momentum equation for the process of restitution on the ball A, and MBU plus RDT is equal to MBVB. This is impulse momentum equation for the process of restitution on the ball B. Now with the help of these four equations, we can write equation for conservation of linear momentum. Actually, there is no need for this equation to write equation of conservation of linear momentum, because either we assume that external forces during the collision are absent, or magnitude of external forces during the collision is negligibly small as compared to those of interaction forces. The impulse of external forces during the collision can be neglected. So in this way, we can say safely the momentum total of both the balls will remain conserved. But let us write, can we arrive on these equations with the help of these four equations? Conservation of momentum during the collision. Say here, adding right hand members to the right hand members and left hand members to the left hand members of equation 1 and equation 2, what we get? What does it mean? We add the right hand members to right hand members here, and add the left hand members to left hand members of these two equations. What we get? If we add these two terms will cancel, and what we get? MAUA plus MBUB is equal to MAU plus MBU, and here U you can take common, so what we can write? MB plus MA into U. So what we get? MAUA plus MBUB is equal to MA plus MB into U. So what it shows that during deformation period, momentum is conserved. Similarly, by adding these right hand left hand members for equation 3 and 4, we can write the conservation momentum equation for the process of restitution. So this equation here, equation number 5, elucidates conservation of momentum during deformation period. Similarly, adding right hand members to the right hand members and left hand members to the left hand members of equation 3 and 4 we get. So if we add these, if we add left hand members to left hand members, so these two terms will be added, but these two terms will cancel. So what we get here? MAU plus MBU, so we can take U common, so what we get? MA plus MB into U, and here we get MAVA plus MBVB. So what equation we write here? MA plus MB into U is equal to MAVA plus MBVB. We call equation number 6, and that explains or illustrates conservation of momentum during restitution period. This equation elucidates conservation of momentum during restitution period. Here we arrive at very important thing, that at the maximum deformation, this is the momentum, and this momentum is equal to the initial momentum, and this momentum is also equal to final momentum. By this equation we can find velocity of both the bodies at the time of maximum deformation. This information will enable us in calculating so many things, and we'll see later while discussing example problems how this middle term will be helpful to us. From equation 5 and equation 6 we get MAUA plus MBUB is equal to MA plus MB into U is equal to MAVA plus MBVB. So that is a very descriptive equation describing conservation of linear momentum during a head-on collision. Actually, in most of the situation and most of the problems which are asked in textbooks or exams, actually this term is not involved. So we generally in the conservation of momentum during collision, we write this equal to that only. This equation describes conservation of momentum during the collision. The equation can be written in more convenient form as MAVA plus MBVB is equal to MAUA plus MBUB. We call equation A, that is conservation of momentum, means initial momentum at the time of beginning of collision or beginning of interaction between the bodies, is equal to final momentum at the end of collision or at the time of when interaction between the bodies ceases. So that is the equation for conservation of linear momentum. Now, what we can say here it is assumed that no external forces are acting on the system of the two balls, or if generally it is said that there are no external forces, but there may be external forces. Suppose two balls are colliding in air. Even for that collision, we can assume momentum to be conserved. You can see for that collision, gravity is acting, air resistance is acting, but these two forces are so smaller than the interaction forces, so that impulses during the collision can be neglected and momentum can be assumed fairly conserved for that collision. So what we conclude from here, if finite external forces act during the collision, the momentum can be assumed fairly conserved. So that is what is mean. And actually this condition is not usually mentioned. What is mentioned that during collision there are no external forces. So what I am adding here, that even there are finite forces, external forces acting on system during collision. Finite forces means the actually interaction forces acquire infinitely large magnitude. So as compared to impulse of the deforming forces, impulse of these external forces are negligible, so total momentum can be assumed fairly conserved in the presence of external finite forces. Now we have to define another very important term that is known as coefficient of restitution. Actually it is denoted by U, and we have seen that is it is equal to ratio of velocity of separation to velocity of approach with a negative sign, what we have seen in earlier classes. But we try to understand this concept in some more elaborate way. The ratio of magnitude of impulses of the deforming forces during restitution period to that during deformation period is known as coefficient of restitution, E. Actually, this is definition of coefficient of restitution. So what we can write here, E is equal to impulse of R dt upon ddt. So is equal to r dt upon dt. Here I will again mention that these integrals are definite integral. This integral extends from the instant of maximum deformation to the instant when collision ceases, and this integral extends from the instant of beginning of collision to the instant when there is maximum deformation. So that is the fundamental definition of coefficient of restitution, and we try to understand what we can conclude from this. From the impulse momentum equation 1 and 2 we get. So if you recall equation 1 and 2, from 1 you can write value of ddt, and from 2 you can write value of rdt and substitute here. So what you get? Equation 1, just I am again writing here for reference, ma ua minus ddt is equal to mau. So from here what we can write ddt? So ddt is equal to ma ua minus u. That is very simple to understand. Similarly, from equation 2, what we can write? That equation 2 is mau minus rdt is equal to mava. From here we can write value of rdt. So what is rdt? Ma u minus va. Now we substitute these values. What you get about E? Substituting expressions of impulses for ball A during the restitution and deformation periods, we get E is equal to u minus va upon ua minus u. So we call this equation 1. So even restitution period can be defined, restitution coefficient can be defined for ball A only. If you know velocity of the ball A at the beginning of collision, at the end of collision, and at the instant of maximum deformation. By following similar analysis, we can write coefficient of restitution for ball B also. Similar analysis for the ball B yields E is equal to Vb minus U upon U minus Ub. We call this equation number 8. Now what we can do? From equations 7 and 8, we get E is equal to U minus Va upon U minus U, this and equal to that, Vb minus U upon U minus Ub. Now it is very known fact that if we add the numerators and denominator of these two expressions, even we get the same ratio. So what we do, the same thing here, UA minus VA plus VB minus U upon UA minus U plus U minus UB. Now you can see from here, this term U and V will cancel out. Similarly here, this term U and U will cancel out. So what we are getting, A is equal to VB minus VA upon UA minus UB. So that is a well-known expression for a coefficient of restitution. So we arrived on this definition or this formula from the basic definition of coefficient of restitution. Here we can write in well-known form, VB minus VA upon UB minus UA with a minus sign. Why we are written here? Because in this way, it is simpler to remember. What this shows? Velocity of ball B with respect to ball A after the collision. So that is velocity of separation. What is denominator is? Velocity of ball B with respect to ball A before the collision. So that is called velocity of approach. That's why coefficient of restitution is known as negative ratio of velocity of separation to velocity of approach. Numerator and denominator of the above equations are velocities of separation and velocity of approach respectively. So these are the very famous terms. So we have understood why this is called velocity of separation and why this is called velocity of approach. And by using relative motion idea, we can remember this equation very easily. What? Take velocity of separation or velocity of approach with respect to any of the balls, say ball A. So what is velocity of separation? VB minus VA. What is velocity of approach? UB minus UA. Take the ratio and put a minus sign. Rearranging the terms, we get VB minus VA is equal to E, UA minus UB. We call equation B. So we have given number A to conservation of momentum equation and given number B to coefficient of restitution equation in some rearranged form. So these two equations A and B are used to analyze usual problems in head-on collisions. Now we discuss general strategy of solving problems on head-on collision and some more detailed idea of a coefficient of restitution, because usual problems can be solved with the help of two equations, so that is conservation of momentum and coefficient of restitution. But in some problems, the intricate knowledge of coefficient of restitution may be required. Strategy of solving problems on head-on collision. Any problem of an head-on collision can be solved with the help of the following two equations. The first equation from conservation of momentum, that is MBVB plus MAVA is equal to MAUA plus MBUB. We call equation A. And for E, that is VB minus VA is equal to E, UA minus UB. We call equation B. Now if you see these two equations, there are four unknowns. What? Two masses, four velocities that are two before collision and two after collision, and one coefficient of restitution. So in this way we have total 7 variables. In 7 variables we have two equations. So any problems on head-on collision can be solvable if out of these 7 variables 5 are known. Only 2 we can determine. So in this way we can see all variety of the problems. But in some problem, detailed analysis or detailed knowledge of coefficient of restitution is required. So we discuss something more about coefficient of restitution. More about the coefficient of restitution. We first write the formula for E, which we have derived. That is RDT upon dt impulse. That is minus VB with respect to A upon UV with respect to A, or minus VA with respect to B to U with respect to B. Now just see what it shows. Velocity of B with respect to A after collision. It is velocity of B with respect to A before collision. Similarly, we can write velocity of A with respect to B after collision to velocity of A with respect to B before collision. And while we are taking this ratio, put a minus sign. That is impulse of deforming forces during restitution, and that is impulse of deforming forces during deformation. Now we know that how this R and D varies with time. Let us discuss that. So here we take a typical example. how the interaction force F varies with time. Now, say at this moment t is equal to 0, this interaction force or deforming force begins. So this is called beginning of collision. Here it will become maximum. So at that time there will be maximum deformation. Now deforming force start decreasing and there they cease to act. So that is end of collision. So from this instant to that instant is called duration of collision. Similarly here this shaded area. Now that is from beginning of collision to the point of maximum deforming force or maximum deformation. Up to that, this shaded area will be equal to impulse of deforming forces during deformation period. So this will be ddt. And from this instant to that instant will be the period of deformation. Similarly, this colored area, sky blue, will be impulse of the deforming forces during restitution period. So we can write here rdt, and from this instant to that instant will be restitution period. Now here we talk about value of E, that it depends on various factors as elastic properties of material of the bodies, velocities of the contact points before the collision, state of rotation of the bodies, and temperature of the bodies. Actually, how it will depend on velocity of contact point, it requires somewhat attention. It is obvious that E will depend on elastic properties, but how it will depend on velocities before contact? Because velocities of the contact point before collision will determine the amount of maximum deformation. So if amount of maximum deformation is within the elastic limit, E will be 1. If it is beyond elastic limit, E will be less than 1. So E will depend also on the velocity of contact point before collision, and similarly on temperature, because temperature governs the elastic properties. Say a very well-known fact, E is equal to 0. This collision is called perfectly plastic or perfectly elastic collision. In such collision, bodies do not separate after collision. Usually it is called bodies stick to each other. It is not they stick, because there is no force of adhesion between them, considerable force of adhesion. Actually, they move in contact. Of course, they may stick also. And extreme value of E, that is E is equal to 1. This kind of collision is called elastic, perfectly elastic collision. Here, mechanical energy is conserved and kinetic energies before and after the collision are equal. So that is here in perfect elastic collision, there is no loss of mechanical energy. So initial kinetic energy, why we call initial kinetic energy equal to final? Because initially there were no interaction forces between the bodies before the beginning of collision. So there is no question about talking of potential energy. So total mechanical energy is the kinetic energy before collision, and similarly after the collision, the total mechanical energy is the kinetic energy. So during perfect elastic collision, there is no loss of mechanical energy, that is kinetic energy. So in this way, we have something about coefficient of restitution. Now discuss how the impulses of deforming forces during deformation period and during restitution period affect value of E and momenta of the body. Impulses during deformation and restitution period. So for easy reference, we rewrite the equation, say here. Consider the impulse momentum principle on any of the colliding bodies, say A. Deformation period. What is the impulse momentum equation and diagram? Here initial momentum, impulse of deforming force during deformation period, we give it a symbol G of D, because so many times writing this will be cumbersome. So it will be again MAU. So equation is MAUA minus J of D is equal to MAU. Similarly for restitution period, MAU, again RDT, we call it J of R is equal to MAVA. So what equation is? MAU minus J of R is equal to MAVA. So here we are giving impulses to a symbol. Impulse of deforming forces during period deformation, J subscript D, and impulse of deforming forces during restitution period, J subscript R. Adding right hand members to right hand members and left hand members to the left hand members of the above equation, we get If we add them, what you can similarly, JD plus JR is equal to MAUA minus MAVA. That is what it shows. The total impulse during collision, that is impulse during deformation period, that is impulse during restitution period, is equal to change in momentum is decrease in momentum. Initial momentum minus final means decrease. So total impulse during deformation period decreases impulse of the ball A. Similarly, we can write for the ball B. Exactly similar analysis we can follow, and what we get? JD plus JR is equal to MBVB minus MBUA. What it shows? This impulse increases momentum. What it shows? Another way of interpreting momentum conservation. That is, by what amount of momentum of the ball A decreases, by the same amount of momentum of the ball B increases. So we can write it in some other form. Previous two equations explain the conservation of momentum in another way. That is, decrease in momentum of one ball is equal to increase in momentum of the other ball. So it is again another way of thinking about conservation of momentum. So how we can write this equation? That is, JD plus JR is equal to change in momentum of ball A magnitude is equal to change in momentum of ball B. We are writing here with positive sign, so we take here modulus. So it is understood which momentum is decreasing and which momentum is increasing. Again, one very important equation. Deforming forces act on a body in the same direction in the whole process of a head-on collision. Actually, on a body, deforming forces D and R will act in the same direction on ball A opposite and ball B in forward direction. On any of the ball, R and D do not change direction. So from the definition of the coefficient of restitution, what we write? In terms of impulses, we get E is equal to JR upon JD, or JR is equal to EJD. From the definition of the coefficient of restitution, in terms of impulses, we get J of R is equal to E times J of D. Now we use this equation and that equation. What you can see, this equation gives sum of impulses and this equation gives ratio of impulses. So by using properties of ratio and proportion, we can write these two impulses in terms of momentum and E, momentum change and E. From the above two equations, we get J of D is equal to delta PA upon 1 plus E or delta PB upon 1 plus E. We can equation 11. So similarly, what is J of R? E upon 1 plus E delta PA or E upon 1 plus E delta PB. Equation number 12. So sometimes it may be required to calculate impulse of deforming forces during restitution period and during deformation period. So in this way we can find it with the help of change in momentum and knowledge of coefficient of restitution. So you can see how much this coefficient of restitution give information to us. Now we are coming on application of the ideas what we have learned. So let's discuss example 1. A ball of mass 2 kg moving with a velocity 5 meters per second collides directly with another ball of mass 3 kg moving in the same direction with a velocity 4 meters per second. The coefficient of restitution is 2 by 3. Find velocities after the collision. So you can see both the bodies are moving in the same direction and collision occurs, and collision is head-on collision and E is given, masses are given. So we have to find velocities after collision. So it is a very simple problem. Just I have taken this problem to make you familiar of using equation A and equation B. Distinguishing the balls as the ball A and ball B, state of motion of the balls immediately before and after the collisions are shown here. So we draw the two diagrams. One diagram we show state of motion immediately before the collision or at the beginning of collision, and in second diagram we show the states of motion B of mass 3 kg. Now you can see this velocity is 5 more than 4, so there will be collision. Now what will be states of motion immediately after the collision? So VA and VB are unknown, so we show them VA and VB by symbols. Now what we can do, we can write both the two equations, one from conservation of momentum and one for E. From the conservation of momentum, we get MB VB plus MA VA is equal to MA UA plus MB UB. So by substituting values, what we get? 3 VB plus 2 VA is equal to 2 into 5 plus 3 into 4. Just you can see here. So what equation we get here? 3 VB plus 2 VA is equal to 22. Equation number 1. Just see that is 25, 10 and that is 12, so 22. Now we write the second equation from the idea of coefficient of restitution. From the idea of a coefficient of restitution, we get VB minus VA is equal to E UA minus UB. Now we substitute the values. So what we get? VB minus VA is equal to 2 by 3 into what? 5 minus 4. So ultimately what we get? 3 VB minus 3 VA is equal to 2. Here, equation number 2. Now, by solving equation 1 and 2, we can find what is VA and what is VB. From the equation 1 and 2, we get VA is equal to 4 meter per second towards right, and VB is equal to 4.67 meter per second towards right. Here, both the balls will keep on moving towards right. So that was a typical examples, just how you can learn to use these two equations, one conservation of momentum, another conservation that is coefficient of restitution. Actually, I have mentioned earlier that is most of the problems in head-on collision are based on these two equations. And what is in these two equations? There are 7 variables and 2 equations. So any of the 5 will be given and any of the 2 can be asked. Example 2. A block of mass 5 kg sliding with a velocity 2 meter per second on a frictionless floor towards the right collides with another block of mass 3 kg sliding with a velocity 4 meter per second towards the left on the same straight line path as of the first block. Find velocities of both the blocks after the collision. For coefficient of restitution, E is equal to 0, E is equal to 0.6 and E is equal to 1. Here the condition on the same straight line path, it means both the blocks are moving on the same straight line. This condition ensures the collision to be an head-on collision. And we have to find velocities after collision for 3 different values of E. So it will be better to develop expression for velocities after the collision in terms of E, and then substituting these values of E, find the sets of velocities for these 3 different conditions. States of motion of the blocks immediately before and after the collision are shown here. Actually, what is required for a problem, it will be better if you draw states of motion immediately before and immediately after the collision. So these diagram will help us to write the equation. So that is first diagram, immediately before the collision. So this block A with the velocity of mass 5 kg moving with velocity UA is equal to 2 meter per second. Similarly, this block B of mass 3 kg moving with velocity UB 4 meter per second towards the left as given. Immediately after collision, we assume velocity of the blocks VB and VA in the same direction just to avoid any confusion of sign. Now with the help of this diagram, we can write both the equations. From the conservation of momentum, we get MBVB plus MAVA is equal to MAUA plus MBUB. Here we put a minus sign because it is opposite. Now, so substitute the values. So 3VB plus 5VA is equal to 5 into 2 minus 3 into 4. So what we get? 3VB plus 5VA is equal to minus 2. That is 10 and it is minus 12. So that is equation number 1. From the idea of a coefficient of restitution, we get VB minus VA is equal to E into UA minus UB. Now we substitute values. UA is equal to plus 2 and UB is equal to minus 4. So what we get? VB minus VA is equal to E into 2 minus minus 4. So what we get? VB minus VA is equal to 6E. We call equation number 2, and by solving equation 1 and 2 we get VA is equal to minus 9E plus 1 by 4 and VB is equal to 15E minus 1 by 4. Now substituting different values of E, we can find values of VA and VB for the given values. So for E is equal to 0, you can get that is VA is equal to minus 0.25 and VB is equal to minus 0.25, because if E is 0, both the bodies will move simultaneously. There will be no separation between the bodies, so they must have the same velocity and we are getting the same velocity. So what we get, E is equal to 0.6, V is equal to minus 1.6, you can verify it, and VB is equal to 2 meter per second. Similarly, for E is equal to 1, what we get, VA is equal to minus 2.5 and VB is equal to 3.5 meter per second. Now let us discuss the next example. Example 3. Two identical balls A and B make a head-on collision while moving with the velocities UA and UB in the same direction. Coefficient of restitution is E. Part A. Deduce expression for velocities of the balls after the collision. So how we'll proceed here? We again make the diagrams immediately before the collision and immediately after the collision. Velocity of the balls immediately before and after the collisions are shown here. That are immediately before collision, UA and UB, they are in the same direction. And after the collision, VA and VB. What is given? Two identical balls. So their masses are equal. Now we can write from the conservation of momentum equation. What we get, MB/VB plus MA/VA is equal to MA/UA plus MB/UB. Now we substitute the values. What MVB plus MVA is equal to MUA plus MUB. So throughout the equation we can cancel M. So what we get? VB plus VA is equal to UA plus UB. Say equation number 1. Similarly, for coefficient of restitution, what we can write? From the idea of a coefficient of restitution, we get VB minus VA is equal to E UA minus UB. Equation number 2. And by solving these equation 1 and 2, we can find the two unknowns VA and VB. From the equation 1 and 2, we get VA is equal to 1 minus E by 2 into UA plus 1 plus E by 2 into UB. And VB is equal to 1 plus E by 2 into UA plus 1 minus E by 2 into UB. So that was part A. We have obtained expression for velocities after the collision. What is part B? For a perfectly elastic collision, what do you observe? And for perfectly elastic collision, we have to substitute E is equal to 1 in these two equations. So once we substitute E is equal to 1, this term will become 0 and this term will become under bracket 1 UB. So VA will be equal to UB, and here this second term will be 0 and this will be UA. So VB is equal to UA. So what we get? Substituting E is equal to 1 for the perfectly elastic collision, we get VA is equal to UB and VB is equal to UA. It means velocities are being exchanged. So it is a very well-known fact, and we have to use it several times, that when bodies of equal masses make head-on collision, perfectly elastic head-on collision, they exchange their velocity. So what we conclude? In a perfectly elastic head-on collision, bodies of equal masses exchange their velocities. Actually, this is the idea, or this is a result which we have to use several times. So please keep in remember what? During a head-on collision, perfectly head-on collision, bodies of equal masses exchange their velocities. So we come example 4. Two balls of masses 2 kg and 4 kg moving towards each other with the velocities 4 meter per second and 2 meter per second respectively on a frictionless surface collide head-on. After collision, the 2 kg ball returns back with the velocity 2 meter per second. So what is given? Before collision, both the velocities are given, masses are given. And after the collision, it is given that the 2 kg ball returns back with a velocity of 2 meter per second. So what we have to find? Find velocity of 4 kg ball after collision and the coefficient of restitution. So again we do what we show the state of motion immediately before the collision and immediately after the collision. So what we can show here, let us see the diagrams. Velocities of the balls immediately after and before the collision are shown here. That is immediately before collision. What is given? 2 kg ball, this one A, and 4 kg ball, this one. 2 kg ball, they are moving towards each other. So it is moving with velocity 4, it is moving with velocity 2 here in this way. And after the collision, what we assume? What is the 2 kg ball, that is A, has reversed its direction and starts moving with 2 meter per second. So this velocity is given. So VA is 2 and VB is unknown. So here in this situation, two things are unknown, VB and E, and all 5 things are given. So we write the two equations, one for conservation momentum, other one for E, and find these two unknowns. That is very easy. From the conservation of momentum, we get MBVB plus MAVA is equal to MAUA plus MBUB. Now we substitute the values. What we get? 4VB plus 2 into minus 2, that is final, is equal to 2 into 4 plus 4 into minus 2, because its velocity was in this direction. This 4 into this velocity here. So what we get ultimately? VB is equal to 1 meter per second. So from conservation momentum, we obtain equation velocity this. Now we know for all the 4 velocities, velocity of both the blocks before collision and velocity of both the bodies after collision. And substituting this, we can find coefficient of restitution. From the idea of coefficient of restitution, that is equal to negative of velocity of separation to velocity approach. So we can write VB minus VA is equal to E, UA minus UB. So 1 minus minus 2 is equal to E, 4 minus minus 2. So what is VB is equal to, we can got 1. And VA is equal to that is minus 2. So 1 minus minus 2. E, what is UA? UA is given plus 4. And what is UB? Minus 2. So what we get from here? E is equal to 0.5 or half. So for this collision, coefficient of restitution is half. Now we have B part for this problem. Find impulses of the deforming forces during deformation and restitution process. Here we have to find what? Impulses during deformation period and restitution period. So for this we can proceed in various way. But how we proceed here? What are the various way? Either we can use the formulas what we have developed earlier, or the strategy how the formulas were developed. Or you can do one thing. You can find velocity at the time of maximum deformation by using conservation momentum. And till that time, what is decrease in momentum of ball A is the impulse during deformation process. Or till that time, what is increase in momentum of ball B? That is impulse of deforming forces during deformation period. And by the same velocity, you can find decrease in momentum of ball A or change in momentum of ball A. That is impulse of deforming forces during restitution period. So let us proceed here. Sum of impulses during deformation and restitution periods are what? JD plus JR is equal to delta PA or is equal to delta PB. That we know from the definition of coefficient of restitution. What we have? JR is equal to E into JD. So what we can write? With the help of the above two equations, we get JD is equal to delta PA upon 1 plus E or delta PB upon 1 plus E. Similarly, that is equation number 1 that we have written earlier. JR is equal to E into delta PA upon 1 plus E or E into delta PB upon 1 plus E. That is equation number 2. Velocities of the balls immediately before and after the collision are shown here. This immediately before collision and immediately after collision that we obtained. This is 1, this is 2 reverse. Now we can make use of these velocities and these relations we can find the impulses. So calculate delta PA or delta PB from the values shown in the figure. So delta PA is what? Equal to delta PB, because change in momentum both the ball in magnitude are equal. So that is 12. We can verify from here. Substituting the above values and E is equal to 0.5 in equation 1 and 2 we get. So here substitute this value 12 and E is equal to 0.5. We get J of D is equal to 8 Newton second and J of R is equal to 4 Newton second. Now you can say their total sum is 12 and again here we get in 12. So that is a check, cross check whether we have done calculation correct or not. Now let's come on the next part. C. Find the maximum energy of deformation. How we can find maximum energy deformation? One way, find velocity at the time of maximum deformation. So at the time of maximum deformation, we can find the kinetic energy of the system and initial kinetic energy and this kinetic energy difference. This energy has gone into deformation. Maximum energy of deformation, UD max, is the energy expended in deformation period till the maximum deformation. This energy is equal to the decrease in total kinetic energy till the maximum deformation. Actually, it is asked maximum deformation, means energy expended. It doesn't mean that energy stored in deforming forces. Actually, that is called maximum elastic potential energy stored. So here maximum energy of deformation is how much energy has been required in deforming process, and maximum is till the maximum deformation. So that will be difference in kinetic energy at the instant of beginning of collision and at the instant of maximum deformation. Velocities of balls immediately before the collision, at the time of maximum deformation and immediately after the collision are shown here. That is immediately before the collision, at the time of maximum deformation both the balls have same velocities, and immediately after the collision that we have obtained one here, and this 2 in reverse direction is given. And with the help of this we can find U. Applying conservation of momentum from the instant immediately before the collision to that of maximum deformation, we can calculate U. So for that we can find conservation momentum. So MA UA plus MB UB is equal to MA plus MB into U. So from here U is equal to MA UA plus MB UB upon MA plus MB. And by substituting value, you can find U is equal to 2 into 4 plus 2 into minus 2 upon 2 plus 4. How 2 into 4? That mass is 2 kg, velocity plus 4. That mass is 4 kg, velocity minus 2 and mass 2 plus 4. So you get 0. So velocities of bodies at the time of maximum deformation is 0. So total initial kinetic energy has been used in the process of deformation. Actually, after the end of collision, you can see both the bodies acquire some velocity. So that kinetic energy is given to the ball because of impulse of the deforming forces during restitution period. Now we can find UD max is what? Summation K before collision minus summation K at the maximum deformation. So that is half MA UA square plus half MB UB square minus half MA plus MB into U square. Now you know that U is 0, so this term is 0, so we have to calculate only this term. So now substitute the values. UD max is equal to 24 minus 0. You can see it is 24 joule. So UD max is 24 joule. So that was how we have calculated the energy that goes into deformation, or energy that is utilized in deforming process. Now we discuss the next example. Example 5. In a free space, a ball of mass small m is moving with the velocity ub perpendicular to the rear face of a steel plate of mass capital M. Capital M is much larger than small m. Denoting the coefficient of restitution by E, deduce expression for the velocity of the ball after the collision. Actually, here we can face a problem while writing the equation of conservation of momentum, because this infinite mass m as compared to this small mass m will make this equation unproductive. But how we can think or how we can resolve the situation? Actually, see in this situation, it is well known fact that the change in momentum of the ball will be finite. It means the ball has received finite impulse during the whole process of collision. It means the plate has also received a finite impulse during the interaction process. Actually, it says that the deforming forces have relatively large magnitude. It is not mean that they have infinite magnitude. If it is said that infinite means their magnitude is infinitely larger than the other forces. It never say that the deforming forces have absolute infinite magnitude. Actually, their impulse has finite value, because you can see from here the momentum ball changes by finite amount. So the impulse of interaction forces during the collision has a finite magnitude. Now this plate will receive a finite impulse, but its mass is infinitely large. So change in velocity of this plate as compared to change in velocity of this ball will be negligible. Actually, this change in momentum of this ball is finite, and so mass is finite. So change in velocity of the ball is finite, so it is observable. So change in the impulse received by the plate is the same. So change in momentum of the plate will be the same as that of change in momentum of the ball. But if you divide the change in momentum or impulse by mass of the ball, that is infinite, change in velocity of the plate will be negligible as compared to change in velocity of the ball. So what we assume? During the collision, the plate remains almost immobile. So how we proceed? The plate of infinitely large mass remains almost immobile after finite impulse received during the collision process. These impulses make elastic deformation and generate elastic pressure waves in the plate. Actually, what this impulse does, it creates here some elastic deformation and creates some elastic pressure wave, sound wave, which will travel in the plate. But of course, it may change momentum of the plate, but as mass of the plate is infinite, change in velocity of the plate will be almost negligible. So initially, plate was stationary. So finally, the plate will also be assumed almost stationary, or stationary for all practical purposes. Effect of impulse during restitution and deformation period on the ball are accounted by the idea of coefficient of restitution. So here the idea of E will help us to find velocity of the ball. So what is idea? E is equal to r dt upon dt integral, and for the ball what will be? U minus Vb and Ub minus U. What is Vb? Velocity of the ball after collision, and U, velocity of both the bodies at the time of maximum deformation, or velocity of the ball at the time of maximum deformation, and that is almost zero because velocity of the plate changes by negligible amount. So this idea helps us here to find velocity of the ball. So we can see here immediately before collision, at the time of maximum deformation, the plate has almost negligible velocity. So the ball will also have almost negligible velocity. And immediately after collision, we assume velocity of the ball reversed. Now we substitute these expressions here or values here. Substituting values from the figure into the given equation, we get E is equal to U minus Vb upon Ub minus U. So put the value E equal to 0 minus Vb upon Ub minus 0. So what we get, Vb is equal to E into Ua. Here we assume the direction to be reversed. So what we observe? that after collision with an infinitely large plate which was stationary, it will again remain stationary after collision. The velocity of the ball gets reversed and becomes e times. So it can be thought that plate is stationary. Because of its infinite mass, it will remain stationary. Instead of infinitely mass plate, we can take here a stationary fixed surface also, and we get the same result. So this we can make a note, because this result can be used several times. So what we can have idea here, velocity of a body after a head-on collision from a fixed surface becomes e times in magnitude and reverse in direction. Now, having studied here collision of a ball with a plate of infinitely large mass which was stationary earlier, now we consider same situation and we take the plate to be moving. Let us see what happens. Example 6. In a free space, a ball of mass m is moving with a velocity ub perpendicular to the rear face of a steel plate of mass m. M is much larger than small m. The plate is moving with a velocity up. Up is smaller than ub, so collision to occur. Denoting the coefficient of restitution by E, deduce expression for the velocity of the ball after the collision. Again here, we can apply the same logic. Because change in momentum of the ball will be finite, so total impulse of deforming forces on the ball will be finite. Similarly, the same impulse will act on the plate. So plate receives a finite impulse during the collision. But because of infinitely large mass, change in velocity of the plate will be negligible as compared to that in the ball. So we can assume the velocity of the plate to be almost unchanged during the collision. So the situation is given here. The ball was moving with velocity ub and the plate is moving with velocity up. And now we apply the logic what we have developed earlier. Due to infinitely large inertia, the impulse received during the collision cannot make any appreciable change in velocity of the plate as compared to that of the ball. Thus, we assume the velocity of the plate to remain fairly unchanged in a collision with the ball. So that was idea we have developed. Now what we can think about, care has to be taken that this is true only for a finite number of such collisions and not for infinitely large number of collisions. Actually, there is a negligible change in velocity of the plate. You can assume that that change is vanishingly small, but during a collision. But if number of collisions are repeated and they become infinitely large number of times, so this vanishingly small change in velocity accumulate, and after infinitely large number of collisions, this infinitely small change in velocity will become into finite change in velocity. So such kind of thing is applicable for a single collision, but not for infinitely large number of collisions. Effect of impulse during restitution and deformation period on the ball are accounted by the idea of the coefficient of restitution. Say E is equal to RDT upon DET. So what we have, U minus VB upon UB minus U, and this equation we use the same as we have done earlier in the previous problem. So that is this velocity VP immediately before the collision. And at the time of maximum deformation, the velocity of plate will remain UP, so velocity of the ball will also be UP. And after the collision, velocity of the ball, we are assuming the same direction, VB, and velocity of plate will remain VP. Of course, velocity of plate has been changed, but the change is negligible, so we assume always UP. Now we substitute values from this diagram into this equation. Substituting values from the figure into the given equation, we get what? A is equal to U minus VB upon UB minus U. So U is UP. And so substitute here UP minus VB upon VB minus UP, and we get VB is equal to minus E into UB plus 1 plus E into UP. So that is general equation. And now we can verify. If UP was 0, you get the same result as we had done obtained in previous part. What? velocity will become e times and reversed. But if the plate is moving, the velocity of plate will be added to this velocity, being 1 plus e times. So that was a remarkable result. Now I'll not recommend you to remember the result. You can obtain the result whenever it is required. Now, having analyzed this situation, let us proceed to an alternate method. What? Reference frame of the plate. Actually, the result of the previous part, problem number 5, is very simple to remember. What? If the plate is stationary, the velocity of the ball gets reversed and becomes e times in magnitude. This idea we can use here as an alternate method. What? If you take a reference frame of the plate, in that reference frame, plate will remain always stationary. So we can apply the same result. What? In the reference frame of the plate, velocity of the ball with respect to plate before the collision will becomes e times and reverse, and that will be velocity of the ball with respect to plate after the collision. And now using relative motion idea, we can find velocity of the ball with respect to ground. So let us see how we proceed with that strategy. In a reference frame attached with the plate, the situation becomes similar to a ball colliding a fixed plate. So the result of the previous problem number 5, can be used. In a reference frame attached with the plate, velocity of the ball immediately after the collision will be e times in magnitude and reverse in direction. That is what? The result we have incorporated from the problem number 5. Now how we can use this idea? We draw the diagram immediately before the collision. This is velocity of the ball with respect to plate. And immediately after collision, this velocity will get reversed, velocity of the ball with respect to plate, and becomes e times of that. So velocity of ball with respect to plate vector will be minus e ub plate vector. Here again, there is no need of vector sign because things are in one dimension, but here we have used vector sign. So this equation is applicable in vector form also for component velocity perpendicular to the plate. So VB vector minus UP vector, that this velocity is minus E UB vector minus UP vector. Actually, we have taken in vector form because when we take relative velocity, now this vector form will make you help when the velocities will be added and the velocity will be subtracted. VB is equal to minus E UB minus UP plus UP. So that is what here we have taken. Now we substitute the values and to find velocity in ground frame. Actually, we have obtained the relation here. So VB is equal to minus EUB and 1 plus EUP. So this relation is similar. Now, as given in the problem, representing the rightward direction by positive sign and the leftward direction by negative sign, as given the problem, because all the velocities given earlier towards right. So we assume right to be positive. So we assume unknown quantity, so we will not put plus minus sign. So we take VB as it is. UB will be plus sign and UP will be plus sign. So what we get? VB is equal to minus EUB 1 plus E into UP. So we got the same result and with much easier understanding. So what is recommended that whenever we have to consider collision of a lighter body with an infinitely heavy body, use the result of problem 5. What is that? Analyze the collision in the reference frame of the heavier body. In that reference frame, what result we can use? Velocity of the ball, relative velocity of the lighter body will becomes reverse and e times. This is the same result as the previous one. So we will summarize this result here. To analyze a head-on collision of a body with another moving body of infinitely large inertia, what we do? First, use reference frame attached with the body of infinitely large inertia. Second, in this frame, velocity of the ball immediately after the collision will be e times in magnitude and reverse in direction. So that is what result of problem number 5. And what is third step? So we have written this conclusion in mathematical form. Velocity of the ball with respect to plate, vector sign is equal to minus E times velocity of the ball with plate before collision. Now employing the ideas of relative motion, we get, so that result we can easily obtain by using ideas of relative motion. So the summary is here. What if this situation is given that we have to find velocities after collision? One of the body is infinitely heavy, then use a reference frame of the infinitely heavy body. Example 7. 3 identical blocks A, B and C are placed in a straight line on a frictionless horizontal floor. The coefficient of restitution between the blocks A and B is EAB is equal to 0.5, and that between B and C is EBC is 1. The block A is given a velocity 4 meters per second towards the block B. Find velocities of all the blocks after all the collisions. So here there may be several collisions between different bodies. So what is recommended in such problems? Try to deduce general expression for the outcome of any collision between any pair of two bodies, and in repeated collision use that general expression. So let us see how we proceed here. So situation is given, block A, block B, block C. They are identical in mass, just equal masses are given just to simplify the calculation. And this is given initial velocity 4 meters per second. Collision coefficient or restitution coefficient for A and B is 0.5 and for B and C is 1. There may be repeated collisions between any two blocks. So it is advisable to deduce suitable relation for velocities of blocks after a collision. So we calculate general relation for velocities after collision between A and B, and similarly after collision between B and C. Collision between blocks A and B. So immediately before collision, we assume some velocity of B, say in this direction, and after collision, V and VB. So how we proceed? Momentum conservation. MB/VB plus MA/VA is equal to MA/UA plus MB/UB. Now we substitute values as masses are equal, so the masses will cancel out. So what we get? MVB plus MVA is equal to MUA plus MUB. So after cancelling mass, what we get? VB plus VA is equal to UA plus UB. That is equation number 1 from conservation momentum. And second equation we write from coefficient of restitution. What is that? VB minus VA is equal to E times UA minus UB. We call equation number 2. From equation 1 and 2, we get VA is equal to 1 minus E upon 2 into UA plus 1 plus E upon 2 into UB. And similarly, what is VB? 1 plus E by 2 into UA and 1 minus E by 2 into UB. Same result, same expression we obtain for the collision between B and C. So we rewrite these expressions for both the pairs of collisions. For collision between A and B, we use the relation what we have obtained and we put the value of EAB is 0.5. So what VA was we had derived? VA was 1 minus E by 2 into UA plus 1 plus E by 2 into UB. And what was VB? 1 plus E by 2 into UA plus 1 minus E by 2 into UB. Now substituting E 0.5, what we get? VA is equal to 1 by 4 UA plus 3 by 4 UB. And what is VB? VB is 3 by 4 UA plus 1 by 4 UB. And for collision between body B and C, E is equal to 1 and masses are equal. So we can use the fact that they will exchange their velocity. Of course, we can use similar relation, but here it is easy to write from exchange of velocity. So what will be VB? VB will be equal to UC. and VC will be equal to UB. So they will exchange their velocity. Now we can see from the given situation that first collision will occur between body A and B. And let us write what is the velocity immediately after collision. After the first collision, that is between A and B. Initial velocity of A was 4 and UB was 0. So now substituting this value here. So 1 by 4 into 4 plus 0. So it is 1, and it will be 3 by 4 into 4 plus 0. It will be 3. So let us calculate here. 1 by 4 into 4 plus 0 is equal to 1 meter per second, and VB is equal to 3 by 4 into 4 plus 0. So that is 3 meter per second. Now we show these velocities. So block 1 will be moving with 1 meter per second, block B will be 3 meter per second, C is raised. So now from here it is visible that second collision will take place between B and C. After the second collision, that is between B and C, here we can use, as I have told you, that we can use the idea of exchange in velocity because it is perfectly elastic collision between identical masses. So after collision, we can see the block B will be at rest because C was at rest, and block C will be moving with initial velocity of B, that is 3 meter per second. So VB will be 0 and VC will be 3 meter per second. Now we show these velocities in the diagram. So A will be moving at 1 meter per second, B will be at rest, and C will be 3 meter per second. Now this situation shows that next collision, that is the third collision, will take place between A and B, and for that we use again the same relation. Now you can see the advantage. Why I have developed these general relations, because we have to use 2 times. After the third collision, that is between A and B, so we substitute UA is equal to 1. So what if VB is equal to 1 by 4 into 1 plus 3 by 4 into 0. So it will be 1 by 4 meter per second. So VA is equal to 1 by 4 into 1 plus 0, that is 1 by 4 meter per second, or 0.25 meter per second. Similarly for VB, 3 by 4 into 1 plus 0, so it will be 3 by 4 meter per second, or 0.75 meter per second. Now we show all these velocities and let us see whether further collisions are possible or not. 0.25, 0.75 and 3. Now you can see no further collisions are possible. No further collisions are possible. So after total 3 collisions, velocities of the blocks are as shown in the figure. Now just we have taken so many examples. Of course, these are not very advanced examples, but typical examples. These examples I have taken just to make you understand what idea we have developed regarding collision. Can we use those ideas or not? Of course, if you understand these problems very well, you can attempt any kind of problem. Now let us take a next example. Block A moving with a velocity u makes a head-on collision with the block B that is placed in a contact with a block C on a frictionless horizontal floor. The coefficient of restitution between the blocks A and B as well as that between B and C is equal to 1. Find velocities of all the blocks after the collision. Actually, this situation is given. This block collide here with B and B is in contact with C. So here we can think what kind of collision it is. Whether for the second body we take combined mass. Of course, there is a confusion. Some students think that for this collision we take a combined mass of B and C, but it is not so. Actually, collision is governed by the deforming forces during the deformation process, and that lasts in negligibly small time. Actually, these deforming forces as a pressure wave will transmit in the body B, and then their interaction between B and C will begin. So for this interaction between A and B during deformation, there is no interaction between B and C. So we have to calculate, we have to consider first collision between A and B and what velocity B would have acquired from first collision. With that velocity, B will collide, interact with C, and here we next consider collision between B and C. So in such situation, what consider collision between the first pair, and then or you can say in other words, assume B and C were not in contact. So what velocity B would have acquired after that collision? Assume that B will collide with C with that velocity. So that is the idea behind such situations. The first collision occur between the blocks A and B. As it is a perfectly elastic collision head-on of equal masses, the blocks exchange their velocities. Then the second collision occur between the blocks B and C. This second collision is also a perfectly elastic collision head-on between equal masses. So again velocity exchange will take place. So what will happen? Thus finally the block A and B will be at rest in contact with each other, and block C will be moving with the velocity u as shown here in this diagram. Actually here I have taken for simplicity E is equal to 1, what is the equal mass, because in purpose of this problem is to explain how we tackle such situation. I will again explain here. Whether we take this as a body of 2m and this body m, actually as I told earlier, so many students think on that line, but what is there? Actually collision is interaction between the bodies, that is, it is story of interaction forces. So when A will collide with B, and that interaction is of very small duration. So in that duration, what pressure or forces have been developed in B, they will not be transmitted to that end. So B will not interact with C. So for that collision, it will be independent collision between A and B, and there is no interaction with C. So what we can see in such a situation, when bodies are contact, so assume then separate. So assume it's separate. So what velocity B would have acquired after the collision with A? Next interaction between B and C, it will be treated as collision between B and C with a velocity B, or with the velocity of B, what it had acquired with collision of A. So this is a situation. Now here, this I have taken just to explain the neutral straddle. Actually what was there? Here this ball collide it and assume there were not these three balls. So what velocity it would have gathered or acquired? With that velocity it collide it, and the same thing and same thing. So this idea explains the working of neutral straddle. Actually what is there here? The energy acquired by this ball is transmitted to this ball and transmitted to this ball, and then so this energy transformation takes place. Now with this example I am concluding today's lecture. In the next lecture we discuss about oblique collision. Thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.